Alright, this is an introduction to the basics of snow science, and I'm going to be covering an introduction to snowpack and how the snowpack and corresponding stability changes over time. So this is an image of a freshly fallen snowflake. Hopefully this is pretty familiar, you know, the stereotypical six-pronged snowflake that's very common with fresh snow. However, not all snow is like this. A lot of freshly fallen snow is pretty common to have this structure, but once snow becomes buried in the snowpack, conditions actually change the shape of the snow. So these are two very common snow structures after snow has been buried, and there are a couple different ways in which these form. So on the left, we have faceted snow, and faceted snow is loose, unconsolidated, kind of sugary snow grains, and that's considered to be very weak in terms of avalanche stability. On the right, we have a computer-generated model of rounded snow, and with the rounded snow, you can see it's consolidated snow, and pretty much all the snow grains are connected in some way or another. And that white stuff is obviously moisture, frozen moisture, so snow or ice. And we associate rounded snow as being strong in avalanche scenarios. So first we're going to talk about how snow facets, because faceting poses a lot of risks in the backcountry. It's a very common weak layer that causes slopes to be very prone to avalanches, and understanding its formation can help us prevent unwanted avalanches. So first I'm going to introduce the concept of a temperature gradient, which is essentially temperature changes throughout the snowpack. So this is a temperature gradient in an example snowpack, and at the bottom you can see that the snow is 0 degrees Celsius, and this is because the ground is insulated throughout the entire season by the snowpack, so it stays at a fairly consistent 0 degree temperature. This can obviously vary a couple degrees, but generally speaking, the ground during the winter will always be 0 degrees Celsius. Then at the top here we have this negative 10 degrees Celsius. This is not an objective measurement. It's not always 10 degrees at the top, negative 10 degrees at the top of the snowpack. This is just dependent pretty much on the air temperature, and wind chill can also affect this number. And you can see throughout the snowpack we have varying levels of temperature and that are not necessarily proportional, but somewhat follow with the depth of the snowpack. So at the bottom we have the warmest, and at the top we have the coldest. And so that was an example snowpack, and this is an actual. These are actual readings from a actual snow pit dug. So these are quantitative readings, and you can see the temperature in Celsius along this top here. You can see at the top of the snowpack, it's about a little bit over negative 15 degrees Celsius, and then it gradually becomes warmer until it's pretty close to 0 degrees Celsius towards the ground here. So that's great and all, but how does this apply to fasting? Well, as some of you may know, the air when it's warmer holds more moisture than air when it's cold. So you can see here at 50% relative humidity for both of these air temperatures, the 80 degree air can hold 13.3 grams of water, whereas the 50 degree air can hold 4.9 grams of water, both at 50% relative humidity. And so what this does is essentially creates a pressure gradient, because if you remember the temperature gradient, the warmer areas of the snowpack are at the bottom. And so essentially what that does is it means that there's more moisture at the bottom of the snowpack than there is at the top. And so what this this moisture is going to want to do is move from the area of a high moisture concentration, because the air is warmer at the bottom of the snowpack, and this vapor pressure is going to want to move from higher to lower. So you can see in this simulation here, those little blue particles are water molecules that are moving from an area of higher vapor pressure to lower vapor pressure. And so what this does is it actually causes the moisture in the snowpack to move up. And so what this does is it takes away that crucial moisture that snow crystals need in order to round. Because if you remember, going back to that computer-generated diagram, those snow crystals, the area in between the snow crystals were filled in by extra moisture. And since the moisture is getting sucked out due to this temperature gradient and thus pressure gradient, there's not that crucial snow that's there for that snow to round. So the lack of water causes the crystals to facet because there's no excess moisture that allows them to join together and become more consolidated. So how does snow round? Instead of faceting, this is basically the opposite process. So the slower the moisture exits the snowpack, the faster the snow rounds. And essentially what this means is you want a smaller temperature gradient, which means less change in temperature per, amount of depth that you go down in the snowpack. Because what that's going to do is prevent the moisture in the snowpack from quickly exiting the snowpack before it gives the snow time to round. So you can see here this is somewhat freshly fallen snow, and once it's buried under other snow, that moisture, that excess moisture, kind of fills in these gaps between the snow crystals and allows that layer of snow to become more uniform and cohesive, thus making rounded snow. So you need this high moisture content in order for snow to round. It's pretty much necessary. And the deeper the snowpack, the lower the temperature to depth ratio is, which means it's a smaller temperature gradient, which is good for rounding, as I mentioned earlier, because this essentially insulates the lower layers and prevents, and the smaller temperature gradient prevents moisture from exiting the snowpack as fast, which gives the snow more time to round, so it rounds faster. So now I'm just going to quickly dive into crusts. So there are two main crusts. There are sun and rain crusts. So sun crust is on southern aspects to some degree when it's sunny out, regardless of the temperature. The strong, alpine sun will pretty much always melt that top layer of snow. And what ends up happening is when the sun goes below the horizon and it turns to, evening or night, and temperatures, maybe they stay consistent throughout the day. Maybe they stay below freezing all throughout the day, but they definitely stay below freezing throughout the night. And what that actually means is the sun crust, or the layer on top of the snowpack that the sun melted during the day due to the strong energy and intense energy, it actually refreezes during the night. And so it forms this kind of layer of ice on top of the snowpack, which we'll talk about more when we talk about weak layers and how this plays into avalanche risk. Then this is a rain crust. It's much more smooth, as you can see from the image, than a sun crust. And rain crusts form when a rain event saturates the top layer of snowpack, and then all of a sudden it freezes right after that rain. So it pretty much forms kind of a skating rink like texture. It's just a sheet of ice on top of the snowpack. So now I'm going to talk a little bit about avalanche problems. There are 9 major avalanche problems, and it turns out that not all avalanches are the same. Some avalanches form in other conditions than others. Some are larger than others, that kind of thing. And I'm going to kind of go into a brief explanation of each of the 9 avalanche problems. So the first avalanche problem is a dry loose avalanche. This is a result of unconsolidated snow releasing. And basically this is snow that's not settled into a cohesive layer. And it usually starts from a point and kind of goes in a fan shape from there. So if you imagine sugar, this is pretty much that. It's not faceted snow, but it is very loose, unconsolidated snow that has an easy time kind of cascading down the slope. These avalanches tend to be small, still risky. They can still hurt you and even fully bury you, but generally speaking, in the broader sense of avalanches, these are relatively small avalanches. The next type of avalanche is a wet loose slide. This is essentially a dry loose slide with snow that is higher in moisture content, and this can be caused from a couple of things. One is intense sun exposure, like I was talking about earlier. The other is rain. So both of these, what these do is saturate the snowpack and make the snow wetter, which gives it a higher moisture content. So this, once again, starts from a point and moves in a fan shape down the hill. Another one is a Cornice Fall. So essentially you see this sharp terrain feature here, and this wind is blowing unconsolidated snow grains up and over this terrain feature, which then builds this big lip. And I'm sure if you've gone skiing on steeper slopes, more exposed slopes, you've definitely seen these cornices. And these pose kind of 3 main risks. First of all, if you can imagine you're standing here, it's pretty hard to see where the cornice overhang starts and where you're at risk to kind of break this cornice. And if it breaks and it falls onto the snowpack, these things can be enormous. They can be 30, 40 feet tall, which you could definitely sustain major injuries from that. Another risk is if you're sitting beneath a cornice and the cornice breaks on top of you, it's obviously going to fall on you. That can be a tremendous amount of force and can really seriously hurt you or even kill you. And the third and often overlooked danger about cornices is if this cornice were to fall, natural or human trigger, it could fall into the snowpack, and the force of that cornice fall could actually trigger other avalanches beneath you, which you don't want to get caught in that. So I'm going to talk about weak layers, and you may be wondering why I said there were 9 avalanche problems, but I only went through 3, and that's because the other 6 avalanche problems, they all involve this thing called a weak layer, and a weak layer for these 6 avalanches are crucial for the avalanches to happen. So weak layers, essentially, in a one-sentence summary, they're layers in the snow that serve as points of failure. So there are a couple different types of weak layers. The first weak layer type is a collapse of a weak layer in the snowpack. So you can see here there are these very fragile snow grains sticking up, and I'll explain what these are in a second. But you can see they've collapsed here. And that is, if you can imagine, if this is on a little bit steeper of a slope, these collapsed snow grains with the weight of a snowpack on top of it, it's very easily for that slab of consolidated snow on top of this weak layer, this slab here, to kind of break off and trigger an avalanche. So one of these types of weak layers are facets, which I talked about earlier, the kind of that sugary, uncohesive snow. Here's a close-up image of a facet, so you can see it's a little bit pointy on all aspects, and it's very hard for facets to consolidate once they're already faceted. And so essentially this acts as a weak layer by an analogy I like to use. They're kind of like ball bearings. They provide not a lot of structural integrity to the snowpack, and it allows heavier slabs on top of the facet layer to kind of slide off of them. Another type of that first weak layer is Surfaceor, and Surfaceor is basically the frozen equivalent of dew. So on cold, clear nights on top of the snowpack, this moisture is going to be attracted to the cold surface of the snow. What that's going to do is form these intricate crystals, which you saw in that first image I showed of a weak layer. That was actually Surfaceor. And so the problem with Surfaceor is there are these very delicate crystals that don't have a ton of tolerance for pressure being put on them, but they can be buried beneath snowfall like this. So this is a layer of Surfaceor here that has been buried underneath more snow that's fallen on top of it. And the really risky thing about Surfaceor and later buried Surfaceor is that it has they're hard to trigger naturally because snow, obviously it doesn't put a tremendous amount of load in a very short period of time on the Surfaceor. So the Surfaceor can actually withstand a larger load than it should be able to, just because that stress onto the layer is being added very slowly. But that also means that they're very, very, very easy to trigger with external force, such as a skier, a Cornice Fall, even like a rock falling on it could trigger this layer, because all of this stress has been built up on top of the buried Surfaceor, and it's put a lot of stress on that layer, which lowers the tolerance of the amount it takes to trigger that and collapse that layer. So speaking of trigger, I'm going to talk about trigger points really quick, which are basically areas where the stress on the snowpack is greater than in other areas, meaning the tolerance for that layer to collapse is smaller. So this kind of relates back, remember, to the weak layers, because these all contribute to making a weak layer even weaker and easier to trigger. So the trigger point cause number 1 is the weak layer is especially weak. So this could be Surfaceor, this could be really, really unconsolidated facets. Any weak layer that's extra susceptible to sliding has a lower pressure tolerance before it collapses. A second trigger point cause is that the stress on the weak layer is especially large. So you can see here this particular avalanche, it was in Montana, and it slid on a weak layer. And it wasn't because this weak layer was particularly weak, but it was actually because, as you can see with a human for scale, that's a 6-foot tall human for scale. You can see that the amount of snow that was resting on this weak layer was tremendous. And so it actually lowered the tolerance that this avalanche needed to trigger, because the crucial amount of stress that the weak layer needed to collapse was already, most of the way completed by this insane amount of stress on the snowpack from this large amount of snow on top of the weak layer. And a third trigger point cause is the slab on the weak layer is especially thin, because essentially what this means is that the amount of force needed to trigger the weak layer is a lot lower, because the force it takes to trigger a weak layer must be enough to permeate down into the snowpack to transfer that energy to the weak layer, thus collapse it. So if the slab is especially thin, you can understand that the tolerance for permeating down into the snowpack, down to that weak layer, is a lot lower. So all three of these things kind of contribute to making a weak layer especially weak. And the weak layers, they can actually collapse, and the energy of that collapse can travel for hundreds of feet underneath the snow. And so this particular avalanche was actually triggered up here, and the propagation underneath the snow traveled underneath the snowpack and started a new avalanche over here. So this has several implications for avalanches. Obviously, you have to, if you're traveling in avalanche terrain, which I'll get into in a later video, but if you're traveling through avalanche terrain, you don't think you're necessarily on avalanche terrain, but you might still be in avalanche terrain, because you can actually remotely trigger an avalanche without even stepping on the slope. So that's what makes weak layers particularly dangerous in avalanches. And the second weak layer type, so the weak layers, the other weak layers were kind of layers that were susceptible to collapsing. The second is a weak interface between the snowpack layers, and this is really where that sun crust and rain crust concept comes back in to avalanche safety. So you can imagine if there's a very smooth bed surface here with a large amount of snow sitting on top, this interface here, that's not a very strong interface, because the snow doesn't really have a ton to stick on. And so it's actually a lot easier for it to kind of slide off that smoother bed surface, which can be sun crust, rain crust, or this could be a particularly consolidated and tightly packed layer of snow that doesn't really want any other snow to kind of bond with it. So the rest of these avalanche problems are going to incorporate the weak layers that I've talked about. They're all dependent on those weak layers. So this is a wind slab, and essentially what a wind slab is, this looks pretty similar to the Cornice, but what it is a sharp terrain feature with wind kind of transporting snow over this feature and depositing it on the leeward side. And essentially what this does is, as the snow is moving with the wind actually can slam the snow against features and terrain features and other snowflakes. And what actually happens is, if you remember that 6-pronged snowflake in the beginning, those arms actually break off. And so they kind of become mini snowflakes without any arms. And so what this means is, since the snowflakes are smaller, they can actually pack down into a tighter space. So the tighter, the snowflakes deposit on this leeward side in a very, very dense slab. So it's one cohesive layer of snow. Doesn't necessarily have to be sitting on top of a weak layer. It could be a weak or a smooth bed surface. It could really just be regular snow, because this leeward consolidated slab of wind deposited snow is actually so dense that it doesn't need a ton to slide on. So these are especially dangerous in the backcountry, because they're pretty hard. It's easy to forget about them, because even on nights when no precipitation has occurred, there could have still been high winds that have deposited this loose snow that has later become a more cohesive slab onto the snowpack. And so some ways that you can look out for this in the backcountry are features that look smooth and round can often be a sign of this kind of pillow formation almost of the wind slab here. Another slab avalanche is a wet slab. And so essentially how wet slabs happen, this is a cohesive layer of snow sitting on top of the rest of the snowpack, and essentially when moisture permeates down through the snowpack and weakens the interface between this cohesive layer on top and the rest of the snowpack here, it provides the layer on top for a nice convenient sliding surface that makes it easy for this slab here to kind of slide off the rest of the snowpack. So some ways that moisture can permeate down into the snowpack and reach that weak layer are, like I kind of said with the wet loose, You can have extended periods of warming events and sun, and you can also have rain events. And those are the primary two that kind of allow moisture to permeate that low into the snowpack. Storm slab. This is essentially the result of cohesive layers of recent snow releasing. So if you can imagine this snow, which is typically high in moisture content, because you kind of need it to kind of clump together to form a cohesive layer on top of the rest of the snowpack. And essentially there's just a lot of stress on this layer that causes it to fracture on top of the old bed surface. But fortunately, these types of avalanches, storm slabs, only happen a few hours to a few days after a storm before the snow kind of consolidates and stabilizes and does not become as much of an issue. And like I said, the storm slabs kind of occur more when recent snowfall has had a high water content, and so it makes it easier for the snow to stick together and form a cohesive slab. The next is a persistent slab. So a persistent slab is essentially a buried weak layer. So this dashed line here represents the weak layer, and essentially you have a large amount of snow sitting on top of this buried weak layer. So basically there are several implications for what this means. First of all, it's pretty hard to trigger because it can be very deep within the snowpack. That also means that if it were to be triggered, it would be a very, very large avalanche because this weak layer is failing with, it can be several feet of new snow on top of it. Another thing is since this weak layer is buried so deep within the snowpack, it has a harder, or doesn't have a harder time. It changes slowly, so it can gain strength very slowly. So what this means is that these persistent slabs can be avalanche problems for a couple days, a couple weeks, a couple months, or can even last the entire season. So they are very dangerous in the backcountry. The next is a deep persistent slab, which is essentially a persistent slab but deeper. Again, they're even harder to trigger, so the tolerance that this weak layer has is a lot lower, but it also takes a ton more energy to kind of permeate that energy down enough into the snowpack to be able to actually trigger this weak layer. So it can be triggered by a human jumping off a jump. It can be triggered by cornices falling onto the snowpack, like I talked about earlier, that kind of thing. The next avalanche problem is called a glide avalanche. And a glide avalanche, usually what happens is on a smooth bed surface. So maybe this could be smooth granite or grass, or anything that the snow has a hard time kind of sticking to in the first place on the very bottom of the snowpack. Basically, when any moisture gets underneath there and weakens this interface between the large snowpack on top of the smooth bed surface, if it gets weakened, it's very susceptible to sliding. And so essentially what glide avalanches is the release of the entire snowpack. And these typically happen during warm periods such as late spring or early summer, because what essentially happens is throughout spring the entire snowpack is melting due to warm temperatures and intense sun exposure. And so these really typically happen during warm periods because the snowpack has to be low enough for the moisture to really get all the way down to the bottom of the snowpack. So it typically happens when the snowpack is pretty thin, but can still be very deadly, and it's definitely not easy to predict. These can be very unpredictable avalanches, and while they may be small, they can definitely still catch backcountry recreationalists off guard.